I'm recording. All
Yeah.
yours. Yeah, all yours.
All right. Hi, everybody. Good morning. Thank you all for joining. Um, if you are here for the second time this week for math classes, definitely something is wrong with you, but I appreciate it. Okay, so we talked about we're gonna. Okay, so first thing that I wanted to say is, please, if you have any question at any point, just ask, because sometimes it's hard for me to know how you guys reacting to it or what you think about it, because I can't really see or tell. So just ask at any point. Um, so first we're going to do a really quick recap on vectors and what we've done last time. I'm going to show again the light thing that we've done with the directional light and point light. Then we're going to jump onto matrices. Um, so just like a refresher thing, I'll do it quickly. I think it's this one. So we said that vectors have okay. So we said basically that vectors are we can look at it as displacement, right? I just want to also clarify one thing about vectors because I talked to Alexei about it and I think it was a bit confusing. We can define vectors in a few ways. Also a line basically. So we need some either 2 points that we can subtract. So let's say from C to D I have 2 points over here. And if I'll subtract D from C, I'll have this line. And that would be basically my vector. That would be the length and the direction of it. I can also
Are you presenting?
Yeah, I guess you are not sharing.
I'm not sharing this.
That's me.
Great.
Yeah,
Okay.
Sorry, my bad.
Okay.
Entire screen. That's right. Up. Share.
And that's how you do it. Okay, done. Thank you, guys.
All right.
Yeah. Okay, so now I can see it. Is that okay?
Yeah, we
Yeah.
can see it.
All right,
We
so-
can see it.
Again, so let's start again. So I'm just going to do a quick recap on that. We said that vectors are displacement, and they have their own direction and angle, right? That's what we said. And just to clarify, I said that usually there is more than that, but if you're going to define it, then for me in the world, I would either use 2 points, and I'm going to subtract. So in this case, let's say I have 2 points D and C over here. So I'm going to subtract D from C, and I'm going to have this vector, right? That's one way. Another way is I'm going to have a point already, okay, in space, and I'm going to add to it another point, which is B in this case. And as you can see, it controls that. So the combination of those two things are going to be my vectors. Now, there is 2 cases for this. Like sometimes when I'm going to do a lookup in 2D, I'll actually might use those 2 points because they're absolute in space. And that would be my vector drive. Sometimes in 3D, I would maybe use this form. So I would always change between them. Just depends how I need it. But just remember that basically my point or my values are basically going to start at 0, 0, like in this case. And this is going to be the length and the direction. That's what's going to dictate it. Okay? So we can kind of like convert the concept of a point. Let's say just this is a point right over here. And it's just a point. So for me, you can also treat it as a vector. Okay? So just kind of like a quick recap of that. Okay, so this is one thing that I want to say. Does it make sense, what I just said about it?
Yep.
Yeah, cool, okay. So this is one thing. Let's go quickly about the dot product that we talked about. So it's over here. And we said basically the dot product we're going to do basically multiplication. The dot product is actually multiplication. So there is matrix product, there is dot product, there is cross product, there is wedge product. All of them are top of multiplication. And they give us different things because there is no such thing as just doing a multiplication like with 5 multiplied by 6. So in this specific case, dot product, we're going to multiply each component of those 2 vectors, right? And we're going to add them up. I'm going to have this new value. And we can think of this new value as kind of like a percentage of how much they are facing the same direction. Actually, how much they are similar, because it's also about the magnitude as well. So in this case, the magnitude of them, the length of each one is 1. So it's kind of get cancelled, this one thing. You don't have to think about it, and that's just a direction. Okay, so if I'm going to turn it on, is it this one? This one? Yeah. So those 2 lines, if you can see them, the blue and the pink over here, they are being projected. So basically this line is projected over here, and this line is going to project it over here. When I'm saying projected, I mean they're kind of creating this 90 degrees angle or triangle. So if I'm going to look over here, let me turn this on. Yeah, you can see it when I'm saying projecting, you see how it's kind of like dropped in a 90 degrees angle to this arrow over here. So I can do something like that, and it will always be projected over here. It could be different length, different direction. As you can see, of course, this vector goes also to negative, so it's kind of like negative value of that. That's what we said about -1 and 1, right? And of course, other direction as well. So this is going to be projected in that direction, and we can do something like that. Let me turn this one back on. Yeah, so those one are now projected from one to the other, and you can see how yeah, they're affecting. You can also think about them like shadow. So if I would have a point light over here with this 90 degrees, it's kind of like the shadow of this one on that, sorry, from here, point light from here dropping. That will be kind of like the shadow of that. So that's another way to think about it, which we talked about projections and shadows. It's the same thing almost in our concept. And Alexei, I think, mentioned a good point about it, is that they don't have to start from the zero. That's what I want to say again. It's just, we know that they're at the zero, but if I'm going to move it in space, they're still going to, the projection isn't going to stay, right? Because we don't care about the position, right? They are basically relative in space now. So we can just move them, and as you can see, as I'm going to move the angle of them, the projection would change. And you can see as this one is getting projected over here, this is the length of it. And this is the negative, of course, because they're facing different directions. And this is what we've done with the light. So my normal and my direction of the light don't have to be, of course, in the same 0, 0, right? Just the concept of the vector, that we don't care where they are in space, we just want to know how much they are similar to one another as a direction and angle. So is that cool? Is everybody on board with that? It makes sense? Any questions about it? Because I think I took too fast. All good, yeah?
Good.
Okay, cool. I'm just checking my notes. Okay, so let's jump into Nuke. I'll show quickly before this thing. I'll go and show quickly what I've done over here. I don't remember. Oh yeah, okay, this one. So we set for this result, right? We have two objects in space, right? And maybe I should do it like that so we can see them both. It'd be nice. Yeah. So we have those two objects in space, and I'm looking right now only on the normals. So it's just a direction, it's just vectors, right? They have just the kind of like, they're all magnitude of 1. It's kind of like they are normalized, as we said before. And I'm going to do a dot product over here with the direction of the light, which is also normalized. So as we're looking at the dot product of both of them, we're getting this kind of like result. And I can move it based on this direction of the light as I'm rotating over here. To reiterate over here, the red, green, and blue are the input from the RGB, from the render. And for us, the equivalent for a vector, which is the x, y, and z, and the L represents the light direction in this case. So x, y, z, multiply each component, relative component, so the first component, 2 of them, the second component, the 2 of them, and the third. And we combine them, we get a dot product. That's what we saw before. Is that cool? No?
I think what is important to remember is that Lx, Ly, Lz, it's not the position of the light, if I'm not mistaken.
No, there is no light in the scene right now, like not a nodal light. It's the concept of where the light would come from. It can come from whichever direction. In this case, we're just using an axis. We can actually just write whatever number we want. We don't really care about it. But we are using, for us, it's just symbolize the direction of the light. Not the light, not like light node of Nuke, like not this. I'm not talking about this. I'm just talking, this guy just tells us where the direction of the light should come from. Does that make sense? Or?
Yeah, but didn't you show us the kind of like where we're taking this?
Yeah, we'll see it in a bit in the matrices. I'm going to break it down in a bit. I'm using this one. You shouldn't worry about it right now. Okay. This is, of course, angles. Yeah, absolutely right. This is not, I'm not multiplying 60 over here and -10. I'm actually multiplying a vector. This is angles, not a vector in this case. I mean, it could also be a vector, but it's not a vector in this case. Our vector is normalized. It's actually those values. We're going to see it in a bit in matrices, what it actually means and why it's here. So those values are, it's not those rotation values. It's just a vector that points to us in the direction of the light. Okay, those angles are being converted into this vector essentially. So if that makes sense, yeah, cool. And then we moved into point light, which is now we have an extra thing that we have to do. If before we only have like 2 vectors, now we have to create this new vector, that we're going to replace with the direction of the light. So we're now going to do per pixel direction of light, which is a point light thing. So it's not an overall light direction. And if I'm going to go over here, let's look at it from this thing. It's the same thing, I think. Yeah. So as before, we still have the normal, so this didn't change. But now we're going to use the P world. So you see the dragon looks differently. It's in a different position. Again, if you're unfamiliar with that, every pixel over here represents a position in space. Almost a vertex in our case, basically, or vice versa, like from the render basically point of view. So we can do manipulation in it, and then we can put it back into our system, in our scene. So we took this P world, right, and we subtracted from it the position of the light. I don't know if you can see, this is the light that we have. I think it's actually this one, yeah. This is the pointer that we have. Again, we are not actually using the light. I can do it like that. We don't actually use the light. It's just symbolic for us to think about it like that, okay? I'm not actually lighting the scene with it right now. So I'm taking this and I'm subtracting. So I'm doing, I don't know if you can actually see it. Yeah, I'm just subtracting the light from the red, green, and blue, and it gives us this kind of like new position. Now, if you want to think about it, I haven't showed it last time. It's the same thing as doing, I'll do a transform geo just to make more sense, because I think maybe there was a bit of confusion with that last time. If I'll take this transform node, okay, I'm putting it on the entire scene, and this is my position of the light. Put it over here, and I'm just going to subtract, right? 1 and 2 and 3. So essentially, this result over here, ignore this right now, this result of the new position of them is equivalent to this basically values over here. So they're the same, right? So basically I'm transforming, without doing that, I'm transforming the same thing that I'm doing here, I'm actually just doing per pixel. So I'm not really shifting the geo itself, I'm shifting the information of it, which essentially is the same thing. Does this make sense? And to see it, we can also do something like that. If I'll go over here, yeah. So there is no light over here. Essentially, we are doing something like that. Again, ignore this guy. So this is our position of where they were before, and then the subtraction. Now, before there was a question, but as you can see, it's actually flipped from what I just showed you. It's in the other direction. Before it was shifting to this direction. It's because we are cheating, right? We need to have the light direction basically facing the same direction as the normal, right? Not actually like that. So it's kind of like we are tricking. Remember that? That if it was actually facing the same way, we would actually get -1 because it's actually the opposite direction. So we're actually negating that, okay? So this is what we see, and then we are normalizing that, so we're getting this result over here. And as you can see, so if I look at those values over here, from here, yeah, this is the normalized one, okay? Now, as you can see, everything now falls on a sphere, right? And it makes sense because that's what I said. We are normalizing. Every vector now have a length of 1, which means it could be called the unit sphere, and it will be basically that all of the boundary of the entire sphere falls on basically 1 unit. So every vector will touch this boundary, right? And right now it will only have a direction and not magnitude. Does that make sense? Confusing? No? Yeah? Okay, good. And then we're using this information to do our dot product, okay? So it's going to be per pixel instead of just one directional light. Sorry. And we have basically this guy, and I can go and, of course, move it to different direction and get a different kind of light. You can see how different this one is changing based on that. And I'll just say that quickly that this thing, by the way, can also be thought as a almost like spherical projection. I'm not going to go and fall into that, but if you would look at the scene, from a projection of spherical in this kind of render, I hope it won't crash. Yeah, spherical over here. I think I just killed it. No? Okay. Yeah. So this spherical, if we'll actually put one on the other, they will actually be the same in the scene. So this guy, this is a spherical world. They will actually sit in the same place. You can actually see, I don't think we can actually see it right now, but they will sit in the same place. Less important. And then, I didn't mention, but as I was doing over here, I didn't mention it last time, I think, or maybe I created some confusion. I didn't normalize. So this one is doing the normalize. As remember that we have this Pythagoras over here. So x squared, y squared, z squared, and then square root of all of them give us the magnitude of the entire thing. And we're dividing with that. That's the normalize. I didn't say that I'm actually shuffling it into another channel. So I have just the magnitude, not the normalized one. So if I want, I can actually reverse that. If I'm going to multiply everything again with this magnitude, I will get again the original vectors. The reason I did it is because now I can actually create a fall-off, right? We know that basically light is getting weaker and weaker as we're moving away from the light. So in this case, that's what I want to show. Let's look at this one. So in this case, I'm actually shuffling back the channel that I'm using. In this case, it's called mask. It doesn't really matter. I just shuffle it into a different layer. And I'm going to do the inverse of it because distance as we are closer, it's a small number, and as we are really far, it's a big number. We want to do that the other way around. We want to have a big number when we are close to it, so it's very bright. And if it goes away, we're going to do it very dark. So I'm going to do 1 over. I'm reversing that, like with depth. And I'm multiplying with that, and this gives us the illusion that light is fading out. So you can see the difference from without it and with it. Oh, sorry, and with it. So this dragon is actually a bit darker because the light is somewhere over here. Does that make sense? Questions? Yeah? No? Not sure? Yeah? Oh.
I've got a little question.
Yeah, sure.
So you're using the dot matrix to normalize, and you're using Pythagoras to take out the length of the vector?
Yes, exactly. So Pythagoras, if you think about it, theory is basically what allows you to know the length of a vector. I don't know which one.
Yeah, because you have x and y, and then you've got the c, or a.
Yeah, exactly. So you can think about it as basically this would be our maybe a and b. Pythagoras said that basically a squared over here and b squared equal to c squared, right? So a squared plus b squared, and we know this because it's the x and y. This is the x and this is the y and this is the x. So squaring them, and then this will give us actually this area, okay? Oh, sorry, the length, not the area of this basically vector, right? So if I'm going to rotate this vector, not changing anything, I'm just going to rotate it, it will be actually this in length, right? This guy. Does it make sense?
Yes.
Yeah? Okay, cool. Maybe I should have talked more about it. Actually,
No. It's just it's just you normalize, basically. You throw away the length by normalizing.
Normalization just, I think there is different type of normalization, but normalization just means we're going to put it in a space that is convenient for us. And for us, it's very easy to work with vectors if they just have length of 1, because then the length doesn't change some computation that we need. It doesn't kind of like skew it. Okay? So first
but then Pythagoras is different because the length is...
No, we're using Pythagoras. Before we're doing the dot product, the dot product would get skewed if we're going to use a vector that have more than one length, or actually different lengths of 1, even smaller. So before we're going to do the dot product, before that, we have to normalize it. We have to make it at 1. We use Pythagoras to normalize it. The way we do it is we are computing what the length is with Pythagoras, dividing each component with this value, with this basically this guy, right, the length of it, and that would scale it down to be 1, right? Because if with the length, this is going to become 1 because it's with itself, and those values would get scaled the same proportion in the same way, and now we have basically a vector that it have only a magnitude of 1. So now we can only work with the direction and the angle of it. Does it make sense?
And the normalization is basically what we're doing is moving the circle to have
we're scaling it.
0 and 0.
We're scaling it, yeah. We're just scaling it basically.
Scaling it you did with Pythagoras.
Yeah, exactly.
And
Pythagoras didn't do
Pythagoras
didn't do any scaling. It just told us what the length is. That's all it is. So Pythagoras just tells us the length of the vector itself. Okay, that's what it tells us. We're using the length to divide it with each component of the vector, and this operation is basically normalizing us, this vector.
Okay.
Is that make sense?
Okay.
Are you still confused?
Yeah. And the dot product is to put us back into
exactly
0, 0.
The dot product is again to get the right angle of that, basically to know how much they are different or not different.
Okay. Okay.
Yeah?
Okay, that's a different thing. Okay.
Yeah. Does it? Should I show another diagram, or are we good?
No. Go
Okay.
go for it. It's
Okay.
I think it's getting there.
Maybe I have it over here. Yeah, so I have this vector. I don't think you can see it over here, but basically I'm doing kind of like a Pythagoras over here, getting the length. I'm dividing, so it makes it the same direction. It's something like that. And then I'm doing a dot product with the other one, and then I have the direction. So I have to separate those two things so they won't get skewed. Okay, so...
Okay.
Yeah,
Yeah.
we good? Okay,
Yeah.
cool. So, about the distance, everybody is on board with that? Yeah, so we had a distance,
Yeah.
we kind of like made it kind of like fade out, or kind of like as we're getting away. There is an equation to how we think of the distance of the light. We don't really care about it right now. It's just going to be usually 1 over like the distance squared or whatever, but we don't really care right now. Yeah, so all good. Can we move to matrices? That makes sense, everything? Yeah, cool. So the first thing that I'm going to talk about, let's look at maybe this one like that. Oops, sorry. And I want to have this guy. Sorry, too many tabs. I think it's this one. Yeah. So matrices, which looks like that. So today we're going to deconstruct this specific matrix. Okay, and it have different names that I'm going to mention in a bit. So the first thing. This matrix lives, if you don't know, this matrix lives in an axis, or any axis basically, so camera, light, whatever, they're all the same thing. We have two inputs over here, two knobs that called local matrix and world matrix. I can open them like that, and I have two matrices over here. As you can see, I'm printing them over here, so you can see them just in a very big way, those numbers, so it won't be an issue. And we have local matrix and world matrix. So this, first of all, introduces the concept of concatenation, and local space and world space, okay? So in Nuke, in this case, every axis have both, or we can see them both, because the first one, the local one, will just show us the local transformation that this axis is doing. So only this. It doesn't care about any other axis. That's what it means. World matrix would show us concatenation from previous axes plus this axis. So if I'm going to put some values over here, I'm just going to change it. I'm going to do something like that. And you can see those two values are the same because it's not concatenated to anything before that. So in the meantime, it just doesn't do any other changes by itself. But if I'm going to put another axis above it, and I'm going to change it as well, now you can see those are different. So this axis is our original axis. This is an axis that comes above it, right, over here. And you can see how this guy, right, the world matrix has been concatenated or been kind of like multiplied together with the local matrix of itself and the world matrix of the one that came before it. Okay, so does that make sense? Everybody knows about these things? Yeah, cool. Okay. Concatenation means for us multiplication, essentially, and we can concatenate as many matrices that we want. And there is, of course, one big benefit to that. Instead of transforming the information again and again with every new axis, if we have like 10 of them over here, it will be very time consuming. We can compress them into one, and then we can just do this movement. So it's way cheaper for us and way more convenient. Okay, so we kind of like can play with that the way we want, and it's easy as we can forget about it. So this is the first thing that I wanted to mention. Let's get back to our matrices, which again, I'm always forgetting which one is it. This one. So first of all, I want you to ignore the bottom row, the 0001. We will get back to it in a bit later and explain why it's there and why we need it. But we can break this matrix into essentially two elements, which is something like that. So first of all, we have this 3x3 matrix, and then we have this vector, a column vector over here. For now, just take my word that this is actually just a translation of the axis. Okay, we can see it over here. So if I'll go over here, wait, this is this one. Okay, so now basically we have a new world matrix, and we have this guy. I'm going to have this matrix. As you can see, as I'm putting some numbers over here, I have 1, 8, and 5. It is the same values over here. So x, y, and z. It's exactly that. So those vectors are the translation. They can sometimes be written as t. And as I said before, because it's a world matrix, it would be concatenating with the one before it. So if I'm going to have another matrix above it, and I'm going to put some other values, maybe negative over here, those are being concatenated together, right? So first of all, this is how we can just get the translation, or where we are falling at the end of all of the matrices where we're going to be. We can just look at this value and use that if we want. Maybe for reconciling different things. All good? Yeah? Cool. Let's look at the second part. So the second part is actually what makes ours rotate, scale, and skew. So this specific matrix, so this, if you look at it, do we have the next one? Yeah. This is a 3 by 3 matrix, as you can see. And this is what's called the linear transformation. Okay? Linear transformation means, it has a few definitions, but for us, there is 3 important things. One, lines will always stay lines. They're not going to go curved or whatever. They're always going to stay lines. Same thing. The second thing is they're always going to stay parallel, no matter what. Even skewing, rotating, whatever. Lines are always going to stay parallel to one another. It means that it's not a projection. They're not going to have this convergence in the end. They're always going to stay parallel. The spacing between them are always going to stay even as well. No matter how much we're going to scale or skew the elements, the spacing between the units are going to stay uniform. And the last element is that they're always going to be revolving the origin, the 0, 0, which makes sense because if you think about it, those are just vectors, right? So they are always in relation to the 0, 0, right? This is the kind of like relationship with that. So now I'm going to show it in Nuke because I think it's going to be a bit easier to see it. So let's move over here. So now we have those guys, right? And I'm going to have a matrix over here. I think actually didn't I do it like that? Yeah, so this is the matrix, okay? Let's see it from here. Yeah. I'm just going to turn off the grid, but let's look at our grid. So I have this matrix over here. Oop, like that. Yeah. And if I'm going to go, I have basically 2 grids, one on top of the other. One is the original and one is going to be ours. And I'm just going to show that as I'm basically rotating them, I'm going to put skew, I'm going to scale it down. It doesn't really matter. The lines, actually I'm going to turn this one off maybe. Yeah, the lines are always going to stay parallel, always going to stay lines, always going to stay evenly spaced out, uniform, and it's always going to stay in relationship to the 0, 0. Okay, so they're not actually translating in space. Okay, we're not actually pushing everything. We're working around this kind of like origin thing. It can also be called a linear mapping, right? This kind of like concept, because they kind of like each axis is kind of like its own kind of like map of linear, and we can kind of like just play with that. Yeah, good. Move on. Cool.
Yeah, there's one thing that I really like to make a like a similar way to understand it. I usually put like checkerboard or a grid node. And just using a transform node, like there's no way to shift the perspective. It's like a similar thing to.
I think it's a bit confusing because we're looking at 3D. I think the best way, I thought about it as well, because when I was like, oh yeah, okay, I know it's like that, so it's fine. I think in 2D world it would be actually much more, because it's the same thing, by the way. This is the same. If I put it over here, maybe let's look at this one. It would be a bit easier. This is the same concept, just in 2D, right? This is still linear transformation. And if I'm going to do something maybe like that, you can see that basically all of the lines are always going to stay linear. It's going to be evenly spaced, and it's always going to say like there is no perspective element over here, and we know that because transform is only giving us that, unlike core mapping. So maybe that would make more sense. Is this make more sense, Adrian?
Yeah, I mean, it's a different way to understand that.
Yeah, because I think in 3D space it's a bit confusing, because if it's rotating like that, then we look at a different angle, and we are looking at a perspective kind of like camera anyway, so it's a bit confusing. So in 2D space, we can see that basically it's like that. Okay, so the next thing is now actually I wanted to mention one more thing. So the combination, so as I said, this is just a linear transformation, this guy over here, this 3 by 3, right? And we can think about them as basically a matrix over here, right? And we can denote it as M, and another column of vector, which is T, the translation. Sometimes they would be written like that, and another fancy word would be maybe augmented matrix, which means kind of like just enhance it. Now the reason we need this T over here is because I said before, linear transformation cannot change the things in space. So that's what we need the translation unit over here. So it's kind of like a cheating kind of like thing that we're doing. This thing together, if you're ever going to read about it, another fancy word, would be called the affine transformation, which is essentially what we're doing with a 2D translation node or in a geo. Affine means we're going to combine the linear transformation, this 3x3, and a translation thing. Okay, that's just called affine. Nothing really fancy more than that. Okay, so if you're ever going to read about it, that's what it means. I think I jumped somewhere. Yeah. So let's now deconstruct this matrix and see what it actually holds inside and what it means. If you remember before, as I mentioned before, over here, I think, is it this one? Yeah. As I mentioned before, let's open it like that, and I'll look at this matrix over here. So now I have another matrix over here, and I have it over here. It's been represented over here by the X, Y, and Z. You can see it. If you remember before, I used the direction of the light, and I told you I'm using actually this guy, right? So some of you can always get, some of you can already guess that each one of those columns are vectors of itself, and it's actually looking something like that. So you can think about them as kind of like three different normals, right? Because we need different three normals because we are in three-dimensional, and each one of them is going to point to a different direction of our plane. Okay, in the X, in the Y, and in the Z. So we have now three normals. And this is what those three guys are doing. And we can also look at each one of them, and they're actually X, Y, and Z of each kind of like vector. Okay, does this make sense? Are you confused? Go back?
No. What are they?
No, I'm good.
Okay.
Normals, okay.
Yeah, no, they're not normals.
Exactly, that's the question. What are they?
First of all, yes, they are vectors. They're not. No, I'm saying normals because they are directional, like normal, but they are vectors of direction, basically in this case. And a way to see it. So first of all, I'm saying it because you can actually see those values over here. We can see as we're looking over here, we can see that this is literally mean x, y, z of a point, which sits exactly over here, right? And this guy is exactly sitting over here, and this guy is exactly sitting over here. So if I'm going to look, from here, I'm going to just put spheres over here on those guys, okay? Yeah, I'm going to put spheres. I just show again, like this doesn't actually have any effect because we're just looking at the vectors. So just to see them, by the way, I'm literally taking those values over here, those guys, and I'm linking them exactly one by one. So this is going to be linked over here. So it's this guy, this is going to be linked like that, X, Y, Z, and same for the rest of them. So now I have each one of them, and as I'm going to change this vector, you can see how basically they are exactly pointing the right direction. So each component basically is a vector that tells the direction of where we need to be on each dimension. That's what literally it means, okay? So those values are literally going to that, and you can see, so one thing that we can see because of the rotation, they are all orthogonal, which means every vector in those three vectors, they're always facing in 90 degrees from one another. Okay, so this is one thing. So those numbers are not random. They literally always will point to this kind of like three kind of like normals that are 90 degrees from one another in rotation, unlike like if we're not going to use any skewing. And wait, I want to show one more thing. I forgot now. What did I want to say about that? I think I forgot what I wanted to say. Oh, I forgot what I want to say. Sorry. Yeah? No? Oh, good. So we are copying that. Sorry, I have now a blank in my head. Okay. I just want to say that those guys are called the basis vectors. Essentially, basis vectors are for each dimension. So if you're going to have just one line and we're going to have just an x, the basis vector is just going to be this x. If we're going to be in a 2D plane, basically, we're going to have two basis vectors. And in 3 we have 3, which is basically each one of them is that. The idea behind them, or the way that I like to think about it, is a recipe to how we're going to move. They are dictating. So this matrix is actually a recipe for us, and each one of them is a quantity of how much we're going to step or move in each direction. Okay, so each one of us is going to dictate that we're going to move this amount of, if I'm going to scale it as well, we can see it even maybe more. So this guy says I'm going to move in this amount of direction to the x, then I'm going to move to this amount of direction in the y, and then in the z. And this is the recipe for that. So this basis vectors just tells us how much we have to move. And this matrix creates for us this kind of like basis matrix. Okay? One more thing that I just wanted to mention, which is less, I think, important, as you can see, there are 1, 1, 1. And this goes back to the unit circle. Those guys can also be maybe unit vectors as well. It just means that this doesn't do anything. Okay? And it's called the unity, I have a blank in my head right now. A unity matrix, which just means it just all diagonal of 1 and everything else is 0, and it just doesn't do anything for us. Okay, that's just what it means. We're still doing actually multiplication inside. We'll show it in a bit, but it just doesn't do anything. As I said before, now we're going to have to add the translation. Have I done it over here? I can't even remember if I have. 1 second, basis vector. You see my head is like, I don't know why, but I feel like I'm forgetting something. Yeah, I feel like I'm forgetting something. This just again shows us that basically again the translation is over here, the rotation is over here, or the scale or whatever it is. Yeah, okay, so now let's move on. So one way that I want to show a bit more is that we can talk about it like that. So these lines are kind of like represented for us this axis over here, which is this guy. Yeah. So one way is to look at it like that, but as before, we can also think about it, because I think it's a bit confusing. We can think about it as like recipe for steps, how much we are moving. So this is another way to look at it. So we're going to step in the z direction 1 unit, then we're going to go up in 1 unit, and then we're going to go 1 in z 1 unit, basically, as a recipe. And I want to show, I think now maybe it would be a good time to talk about matrix multiplication, because it will explain this concept better. So let's go back over here. So we said basically that we have x, y, z. And I said before that we need to ignore for now this one. For now I'm going to stop and just talk 1 second about matrix. Sorry. I had a mistake before. This called the identity matrix. Sorry, not the unity matrix. Identity matrix, which just means it doesn't do anything. It's like adding with 0 or multiply with 1. It just gives us the same result. That's all it means. Sorry. So now let's talk about matrix multiplication, which is what's happening over here. And we actually already know how to do that. If I'm going to now go to the next slide, we have a vector. This is our basically pointing space that we want to translate. And this 3 by 3 is this guy. Okay, so this is our matrix. And to do matrix multiplication, we are essentially just doing a dot product. So as you can see, I'm taking this vector, which is what we want to transform in space. We're going to take this area over here, this basically row, the first row, and we're going to do a dot product with each component again. So we're going to have A times X, D times Y, G times Z, and we're going to add them all up. So we already seen that, right? It's exactly the dot product. It's the same thing. The result of this is going to give us a new X. So as I said before, the basis vectors are a recipe, and we can think about it as basically it will tell us how much we want to use the X, the Y, and the Z, right? That's the idea behind that. So now we can do it to do matrix multiplication with a vector. We have to do this with every row in the matrix. So this is going to give us the new X result. This is going to give us the new Y result. It's the same thing. Column times this vector, dot product, okay? Bx, ey, hz, new result for the Y. Same with the Z. So same thing. And this is how we're going to do it. We can see that basically there is some sort of a pattern. We can see how the X, Y, and Z is kind of like repeating in each basically dot product we're doing, right? Because it's the same vector. So we can also think about it in that way. We can also see exactly how we are using the X component over here and how the matrix tells us how much to use this X component, the X basis vector. That's exactly what we are doing, right? So this guy is just telling us how much, as a recipe. I'm just repeating the same concept again, just to reiterate on that. It's just a recipe to tell us how much we're going to shift in each direction, in each dimension of like X, Y, and Z. Yeah. So kind of like this X, Y, and Z. Any questions so far? Any confusion?
I'm confused.
Yes,
Of course.
please. Yeah.
So A, B, C, D, E, F,
Yeah.
This is X, Y, Z vectors.
Exactly.
That we just had a look. You showed it very nicely. So this will be between 0 and 1. They're normalized, am I correct?
They don't have to be normalized. They can be whatever they want.
Yes.
Normalized just means they don't do anything. And if they are only rotation, they are normalized.
Yeah, but that's what we saw right now.
Yeah.
They were kind of like only rotation. So whatever you're doing, they're just
Yeah.
showing the direction
Yeah.
of the normal. So this is okay, fine. So this is the beginning.
Yeah.
This is so this is a D C. It's the X, then D E F it's Y, and G H I is
Exactly.
Z.
It's yeah. And
Good.
maybe
So this is the three first one. Now
Exactly.
my question is, so can you go back to your and then X Y Z is
our vector.
our vector of and it can be basically
It's when we're transforming every geo. So
it's the transformation.
Exactly.
No, it's
No,
the
no.
transformation.
This is a
It's not.
transformation, right? And this guy is any vertex that we're going to do transformation on. So
Mhm.
if we have vectors of a sphere, of a dragon, of a card, anything, we're going to transform this information with this data. And we said that this information can be either RGB or XYZ. We're just transforming this information that we're doing with this guy. So we're going to reiterate on, we're going to loop through all of our vertices or all of our pixels, and we're going to use this matrix on all of them.
Yeah,
Yeah?
sorry, I'm stupid.
No.
I don't know what XYZ are.
Those guy,
Yes.
those are the inputs. So
So this is,
let's say I have this dragon over here,
yeah,
right?
Yeah,
And it's built from all of those vertices, right?
yeah.
I don't know why we can see it, but it's built from all of those vertices, right?
Mhm.
And our engine would go and take each vertex, and each vertex is being represented by X, Y, and Z, right? So
This position.
it's those guys. We are taking this position, and we are just transforming this. So we're gonna look through each position of a vertex,
Mhm.
doing this, and we're gonna get a new position of where it's supposed to be. Yeah.
Still. Sorry, guys. Stupid guy here. So
I-
the first three things, but they're responsible for the vectors.
The translation of that, right? Well, this is the translation.
But I understood in the beginning that the first three columns responsible for rotation, actually.
Rotation, scale, and skew.
But and the last one, the
It's
fourth
we still don't have it over here. I'm gonna go in a bit about that. It's an additional thing.
Okay.
So this is just the rotation, scaling, and skewing. Okay, and those components just tell us how much we're gonna move. And I laid it out over here like that, so we can actually see that essentially every input pixel or vertex,
Mhm.
okay, we will transform it with this amount, and we can think about it as how much it tells in each component how much we have to move
Mhm.
for each component of the vector. Sorry, like that.
Okay.
Yeah,
Okay.
good.
Yeah, that's good.
Or we can also see the yeah.
I had a question very quickly.
Yeah, sure.
I understand the theory of the matrix and that the column on the right will be created a dot product of the matrices on the left. But if you could just go back to the Nuke matrices layout, please.
This one.
What I missed, similar to what Alexei was just asking, I understand that the column X, Y, and Z, they're the columns, is. But if we just to define the rows, the first row is rotation, the second row is.
Oh, you mean this?
Yes, please.
I don't know. So the entire thing represent rotate. Sorry. I think I can understand. I think maybe the confusion came from. I think maybe because of this slide. Maybe let's go back to this one. Okay.
Yes,
you mean
this one. Please,
I think that's what was confusing. You thought maybe that this is rotation, this is scale, and this is skew.
Well, I understood the first.
No worries. No. The entire thing represents for us the concept of rotating, scaling, and skewing. Okay.
Right.
And it's been basically the build of that, or encapsulating the idea of that, by having three kind of like direction vectors that tell us how much we would move based on that. So this entire thing represents rotation, scale, and skew. I wasn't sure if I wanted to show it. Maybe if we'll have time, I don't know if we will have time to go how it's actually being built, but it's more trigonometry. It's cosine and sine. I know. Calm down, it's okay.
No.
Calm down, it's okay. But basically, this three base, it's not like this is just a rotation. again, as I said, this matrix, right? Maybe I will show it. Just I know I don't want to confuse it, but I just want to show it because I think no, it's okay. It's okay. It will be okay. Is it this one? I don't know which one is it.
I think it's good to show it rather than skim over it because it's the bit that.
Yeah, I can see how there is a confusion of it. This one. Okay, so if we'll do let's say Euler and matrix. So Euler is basically the rotation that we are using over here.
Yeah.
And we are converting these Euler rotations into a matrix value. And I didn't want to go over it because I think it deserves its own class. But trigonometry, specifically for us, cosine, sine, and tangents, is just a bridge from, there's the way I see it, to convert between vectors, so the x, y, z, from angles to the x, y, z, and vice versa. This is how I see those functions, right? The sine, cosine, and tangents.
Yeah.
So if we have a vector, we want to transform it into the angles if we want to use the angles. Or if we're using the Euler angles, the x, y, z angles that we're using, we want to convert it into the vector. Okay? And this is what the trigonometry is actually allowing us to do. So this matrix, as you can see over here, this guy is doing a rotation on the z. Yeah, it says over here. So essentially, this 90 degrees is the angle that we're going to use. So the number that we're seeing over here instead of Nuke, the number that we're seeing on this guy. So let's say over here, I have a number. And we're going to do sine, cosine. I don't want to go into it why exactly it's like that because, again, it's a different class. But it will create for us a new, basically a matrix. And those guys will be now basically our vectors pointing to each. So essentially, we're kind of like rotating these three vectors, right? In kind of like a different position. So does that roughly make sense? Or have the confusion?
A little bit. It's enough for me to hang on to as you continue teaching.
So this guy is not that this is rotation, scale, and skew. I'm sorry, maybe we shouldn't have read it like that. The entire thing represents all of this concept. The entire thing is a linear transformation. And we are the way that we are doing that, we are computing through different trigonometry or different things, we are computing three vectors that tells us how we're going to move in space. And we need three because we have 3 dimensions. So each one of us tells us how much we have to step in each dimension, in each component. That's the idea. I think maybe scale would be the easiest because rotation is trigonometry. If you think about it, actually, maybe I would actually just show it because I think it's very easy to see it over here. If we just look at this one, that's what I want to show over here on the basis vector. I'll do it over here. So I have this right now. I'll do it like that. And I have, maybe, could I still see it? Would it work? Oops, sorry. I don't know if it's the right vector. Yeah, it is. Okay, so as I want to show, I think maybe because scale is the easiest one to see because it's just a number. If I'm going to do 2 on the uniform, you can see now I have like 2, 2, 2 over here. You can see how those vectors just grown, right? Each one of them, the x, y, and z. And you can see how everything just got kind of like more separated and went away on the scale. So the scale for us just lives over here, by the way. Okay? So scale, I think, is the easiest one to see, but again, you can see how. Yeah?
Can I just say something?
Yeah.
Because there's one thing, if you put your uniform scale to 2.
Yeah.
Now, so you can, yeah. So have a look at the world matrix.
Yeah.
Scale represented by the diagonal 3 numbers.
Yeah.
From top left to bottom right.
Yeah.
And transform is represented by the furthest, the furthest 3 numbers to the right.
You mean this guy?
So yeah, you can see it there exactly, and then as translate or transform as you said earlier. So those are the 2 things that are the simplest to understand when you're manipulating your matrix.
Yeah.
And the complicated bit is the rotation.
Yeah.
Because that involves all of it. And if you're scaling something, if you're skewing something, then you're basically not doing a uniform, like what you're doing here. You're doing uniform scale. That affects those 3 numbers you can see in the world matrix there. That's a kind of, at least like what I like to think about is like the 2 simpler things to understand.
Yeah.
It's the scale and the transform. And then when you get into rotation, then it gets more...
I just said that skew, it's not non-uniform scale. Skew is a combination of scale and rotation, by the way.
Yeah.
But it's not necessarily going to be diagonal. That's the thing. Diagonal just means that we're just going to look at those guys. But I don't want you to think in diagonal. I want you to know that each one of them is just component, it's measurement. And I'll show that if I'm going to do rotation over here before the scaling thing, by the way, so let's say I'm just going to do some rotation. Okay, I'm just going to do something like that. Yeah, and I have these weird values again, right? But they're just telling us again how much we're rotating. The scaling factor just scales each one of them. If I'm going to go with a math kind of like thing, you can see they're just being scaled by these uniform values. So it's not just a diagonal, right? They literally just represent this each dimension, and I'm just scaling each one of them with this. If I'm just going to do actually non-uniform scale, you can see how this would only affect the first one, only the x, and this is only going to affect this guy, and this is only going to affect this guy. That's why I said the scaling is the easy one to understand, because it's literally just a multiplication. It's just scaling up a thing, up and down.
Yeah.
Does it help?
Yeah.
Anybody want to ask anything? Yeah.
No, I get a better picture now. I've got a much better understanding after that last 5 minutes of
Cool.
the matrix now. Thank you.
I know those numbers are confusing, but because we are looking just as a number, that's why I want you to see over here. But again, I am reiterating, and maybe I'm not making a good point, but for me, I just have to look at it as the recipe of how much we are moving. How we're getting this vector, again, it's trigonometry in rotation world. I can do another class. I don't think it's actually that complex as well, but I think we're out of time almost, so I want to jump into other thing as well. No, yeah, I'm not going to talk about this right now. But again, this is, by the way, even though it's weird number, they're still orthogonal, okay? And they're still basically going to be 90 degrees. And they're literally, as I'm rotating, I'm literally just telling how much it should be on these numbers. That's all it is. Maybe a good, another thing that, I'll take another minute just to show it over here. Man, too many tabs. Which one is it? This one. Yeah, and basically you can see that I have a vector over here, and those components is basically the numbers that we see in 3D. So in 2D, by the way, if I have a matrix of 2D, those will be the numbers basically that will tell us how much to maybe move or rotate and stuff like that. I'll talk about it another time, but that's the idea. Is that okay?
Yeah, I have so right now, so these guys, there's 3 vectors which showing us basically the direction, scale, and stuff. So the last one is the combination of all transformations. Let's say we have
this one?
Yes, we have 2 axes which are paired together, let's say. So, and then the last one will show us that basically the transformation, first one, multiply transformation.
Talking about
one.
this?
No, the last one.
Yeah.
Because this is transform.
That's what I'm going to talk right now, but that's the next part.
Yeah. So that's something that
okay, so as I mentioned, so I just want to show something very simple over here. So I took like 3 dragons, and it's not a sphere, so you can see the orientation of them. So if I have a matrix over here, I just want to show that, as before, matrix multiplication is just a vector, in this case, dot product. By the way, also matrix multiplication is just a dot product of each vector and column separately. It's the same concept, so we know how to do it. I just put a card over here, and I have a transformation axis over here, okay, which is being shown over here. And I put a dragon, and what I've done is I went to the transform node. I put a transform node 4 times to get 4 dragons over here. And I created a position, so I will tell it where I want it to be positioned. Okay, this is going to be my position. So you asked me before, what is this, right? You asked me before, what is this guy? What is this guy, right? Yeah. So in our case, this is this guy.
Position.
Okay, a position that I'm using, just a it's not a vector.
Position, that was my main confusion.
And I'm going to call the matrix, the world matrix of this axis like that. You shouldn't care about it, it's just for me to call it, okay? I'm just going to call it like that, is this axis. And I'm literally over here doing a matrix multiplication, a matrix dot product. So I'm literally, maybe I should put a sticky note so you can see it bigger. Yeah. So as you can see, or you can't see, I don't know, can you see it roughly? Is that okay? As you can see, I have this position, right? The position that I created is pos X, Y, and Z. Ignore this part for now. And I'm literally doing a dot product with the matrix. I'm actually taking this value, right, and multiply it with the position X, and then I'm adding this time multiply with the second value, and then the Z. So I'm literally doing a dot product over here. Exactly what I shown over here. It's exactly the same thing. I'm literally doing this line, right? I'm doing actually this line. That's what I'm doing exactly over here. And I'm doing it for each one of the components, right? The reason that I want to show it is now I can do it 4 times. Okay, and I have a vector, so I told him to go half because the entire thing is just 1. This entire axis is just 1. It's half in each direction. So I told him just go basically half over here and half on the y, okay? And I took this one to be minus negative on the y and minus negative on the x. And now I can rotate it, and I'm only rotating the position. I'm basically only transforming the position. I'm not actually rotating anything really. So this is a transformation that we are doing, as you can see. So as I'm going to put other values over here, wait, I lost it. Yeah, as I'm putting other values over here, I can compute again a new position. I'm literally doing this slide. Where is it? What have I done? I opened too many. Oh, is it this one? Yeah, I'm literally doing this guy. Okay, I'm literally doing this thing inside of my transformation. I lost something. Where is it?
Guys.
Are you still here?
Yeah.
Yeah.
Okay.
Okay, so I'm literally doing this guy inside of Nuke. That's what I'm literally doing over here. I'm multiplying each one of them with the position that I just created. Yeah, I can literally go right now and do, you know, I'm going to make it like even one. So it's going to be like outside of that, but it's still going to be in relation to this axis. So I'm transforming that. So as I'm rotating it, again, I can do all of these kind of like things. I can also scale it as well. So let's do maybe something like that. I can scale it in each direction. And because I'm putting it into the position of the node, I'm only changing the position of the dragon. I'm not rotating it. I'm not scaling it. I'm not doing anything. I'm just telling it to put it in a different position, right? I'm transforming it. Mm-hmm. Does that make sense?
That makes sense. I just think we're having some confusion with the terms of transforming, because
you're right.
For me, transformation node is not only doing translation, but also rotation, scaling, and everything in this node. So when we are talking about transformation, can mean either doing all these things, mm-hmm, or just translation. So
okay, so that's what I want to say about the next part. That's I want to talk about the next part. So we also have translation over here, right? I think that's what you're saying, and it is part of this equation. That's what I want to just say next. We're still doing a dot product over here, but the reason I didn't put it before is because now we have this tricky thing. So now we have this matrix, right? We have this that doing the rotation, the scale, and the skew, right? And we have this vector, which is translation. So T1, T2, it's just X, Y, Z of the translation that we want to do. But if we're using dot product, how can we actually do that? What is it going to be multiplied with? We don't have any other component, right? We said X times A, Y times D, Z times G. So what is this going to be? And that's why I didn't add it before, okay? Not to add more confusion. So now we are adding, so now we need to basically do this kind of like mathematical trick, okay? And we're gonna, this trick is actually called the Homogeneous Coordination. It's just a fancy name, literally, just to add this thing, which is called W. It's just like X, Y, Z, W, they just added another letter. In some ways, we can call it another dimension. So if we have X, Y, Z, and W, but all those fancy words literally is just a trick for us to create a dot product. Literally, there's nothing really that smart about it or that sophisticated. Usually in the world, when we're doing transformation, we would put 1 over here. So now, if I'm going to put 1 in the end, and I'm going to multiply it, I would also have the transformation in the end. So now I can still do dot product with this matrix and this vector and get that result. The reason, because it seems like now it's kind of like more complicated, why would we even want to do that? The reason is now I can actually concatenate everything together, including the translation. Before this form, I could not add the transformation. The reason, and I think because of the confusion I showed before, it doesn't, the transformation, the linear transformation, doesn't move in space, it doesn't shift everything, doesn't displace it. It shifts around the origin. That's what we are doing, right? We're scaling it, everything is around the origin, right? But now we still want to move it in space, and we could not do it. So this is a trick what we are doing. We have another vector over here, which will shift it for us, and to add it into the equation, because we need to do dot product, we will basically do this trick of basically having 1 over here and multiplying the translation with 1. You can also see it over here. If I'll, in this equation, you can see I'm adding this position W, it doesn't exist over here, just 1 over here, and I'm multiplying with the translation. 1 multiplied with the same thing, it's just going to go to the translation. It's going to shift in space. That's the trick. And that gives us the bottom row, which is this guy. That's why this is 0, 0, 0, 1. It have other intuition. Homogeneous coordination have a bit more intuition for other things as well, for projections and other things. But if we're going to do a dot product with this vector and this guy, we're literally just going to get 1, because x times 0 is 0. As you can see, 0, 0, 0. Everything is 0. 1 times 1 is just 1. So that's why we have this bottom row over here. I think I really confused you with the last part, right? I think everybody just I really threw everybody off.
No, I think it makes sense. Well, what I understand is that everything before that is it's generating vectors with a 0. I mean, everything is relative to 0.
Exactly.
So that's where we get the vectors. But then when we add the last W, then we are not locked to the 0, to the origin, but we can move around.
Yes, exactly. So as you can see, this first part is we're just around the axis. We scale everything is around the origin. That's why I was trying to really explain this concept of the circle of like this 0 origin is really important. That's why I want to talk about it, because we're doing everything with vector around this 0. You cannot just change it in space. Every linear transformation is just about moving around the origin, rotating, scaling, skewing, whatever. To have the trick of also shifting the entire thing together, not rotating, not scaling it completely, we need to have this extra component. So this is called the affine. We're combining the linear transformation with translation. And we're using homogeneous coordination, this trick of W, just a trick, to add it into this entire kind of like matrix form. That's the idea behind that. Does that make sense?
Yep.
Yeah?
Yes.
Yeah?
Yes.
I think we're really out of time. Can I still like 5 more minutes just to see that I haven't forgot anything? No. We have this, and I just want to say that homogeneous coordination have more meaning than just that. Homogeneous coordination allows us to do projections, which means it's not linear anymore. Everything is going to converge into one point. It means that vectors can also be, or this point can also be represented just by vectors. So if you look at this value over here, if I'll just do it like that, you have the entire value. And I literally would just go, I also want to do something like that. It could be actually quite interesting. You can see that actually I can also go and change my vector directly from here. And if I'm going to put these event values, right, I'm actually skewing it right now. And as you can see, I'm doing everything right now on this align this Z, like if I would change those two. So I can do my own thing, as you can see, just by modifying that. But modifying the W component over here, this one, will do an overall scale, as you can see. And the reason for that is because, again, this is projection. We're kind of like dividing. It's, I think it's a mistake even to go into that. But it have other elements. It's not just for that. So it's a mathematical trick for us to get translation inside, but it have a few other tools to do projections and stuff like that. Yeah.
What for me will help, and guys, I think that's something that we probably will do. It's we'll save this project, and what I definitely going to do over this weekend, and I will try to kind of to go these steps myself. But we will share definitely this video and the project files. What is super important to touch that, because there's a lot of this complicated stuff, at least for myself. And I would highly recommend you like to go steps by step that we will prepare, just to try to understand it, like really touch it, because it's I think that will be the very helpful.
I mean, for me, the point was to make something intuitive. So I hope, for me, I don't want to remember what cosine really means, this function of Pythagoras or whatever. I want to get just this intuition of what we're doing, because, you know, that's what I was trying to talk in the beginning of the last lecture in the beginning. I was trying to say that the way that we're teaching it right now, it's too mathematical, and it's too kind of like, just do this, do that, and that's how it works. Those tools are just a way for us to break down reality, or 3Dness in this case, or 2D or whatever, and we can use this tool to manipulate that. That's the entire thing. You can always cheat and go to Google and look for the function itself if we want to do it. It's fine. It's more than fine, actually. You should not memorize it. I just want to get the intuition of that, of what we're doing over here. And I also want to mention that when we use it in camera concept, Camera have another matrix. It's called the projection matrix, which have the ability to transform from 3Dness into the screen space. I'm saying it because this specific matrix, called also the extrinsic matrix, it's just a location in space. It doesn't have the camera itself or the focal plane or the sensor. It's literally just where we are located in space. So all the manipulation that we are doing is just about where we are in space. Yeah. Another word is, we can also call it composition of linear maps, which is how we kind of like manipulate in different directions, different kind of like movement together. So we're compositing, we're kind of like we're merging a lot of like transformation together. I threw another thing together just to make more confusion, just for the fun of it. Yeah. Anything else? Questions? Yeah. Everything is good?
Great job, Eyal.
Great. Thank you very much.
This is a mysterious hole for a lot of us, and just having these basic tools of understanding what are those numbers that are moving and changing while transforming things. I think I got the idea that there is a relationship between X, Y, and Z as a point, and between 2 points there is a vector.
Mm-hmm.
And to transform these things, you can't just do a simple, just add 3 and it'll move by 3. You need to have everything else which is linked to it move in a mathematical way in the matrix.
Yeah.
And the math behind it, the way we translate the matrix into math, actually has to be done so things will move together as I expect them to move.
Yeah. We just said vectors are displacement, so this matrix just essentially just holds 4 different vectors of displacement, right? That's what it is. 3 for each dimension and 1 for translation. So we have 4 vectors to displace everything in space, and essentially that's what it's doing.
Yeah, but because they're all connected, because if I move one element, they all need to be changed.
They have a relationship between them, definitely.
Yeah, this is why you have this whole thing and not just a simple math x plus z, at least x plus 1 thing. So,
Nikolai?
So all these 3D nodes have the like local matrix and world matrix. But why does the transform node not have a matrix exposed? Because it should be the same thing, right?
You asked me this node?
It's too small on my screen, but I guess,
You mean this guy, right? First of all, that's a question for the foundry. I actually thought about explaining this as well, because I think the intuition would be easier to show it on 2D. It's literally the same thing.
It would be like
by the way,
easier.
I thought about it in the beginning, but
understand it in 3D.
But you guys want to talk about 3Dness, so here we go. It's on you, man. Okay. If you want, literally, by the way, whatever we're going to do over here could also be represented in the corner pin matrix, by the way. It's just going to be 3 by 3, not by 4 by 4, because we have less dimension. This is a bit confusing. This column and this row doesn't do anything for us in corner pin and translation. It's exactly the same concept. Where those, if we have 3 by 3, this guy is going to be the translation, and this is going to be the skewing, rotation, and scaling. Yeah. Why we don't have it, I don't know. It's a bit silly. It's the same thing. It's the same question as I don't know why those guys don't have inverse as well in them. Why this guy have an invert, but this guy doesn't have an invert as well. I don't know. Like it's a design. I don't know. They didn't think about it for some reason. I have no idea why.
That's the trick of just like creating an axis and linking the matrix of the axis to the corner pin.
Yeah.
And then you can use the axis translate and rotate and stuff to corner pin it kind of.
So I'm working on a tool that I hope to get it released. Like it was like 6 years ago, but maybe at some point I will get it out. Which is the ability to actually concatenate all of them and see the metrics as well, which is I think what you want essentially. And you can concatenate, because essentially that's why you can, by the way, concatenate all of those together, because it is essentially just one matrix. It's the same as putting a lot of axes. So corner pin, transform, maybe reformat as well. There is a few others that I can remember right now, but all of them are just 2D transformation, the same as the axis. And each tool just gives us a slightly different way to play with it, the way that we want, right? So I'll direct your question to the Foundry, but I hope it makes some sense.
Just one little thing on that last point. There's one thing that I find quite interesting is that when it comes to concatenation,
yeah,
you know, it's simple because you're using this linear transformations.
Yeah.
And as far as I understand it, concatenation works per channel and with no masks. Because if you were to change something in one channel but not in the other, it's no longer linear. And the same thing if you put a mask in, and you know, if you have like a transform mask node, for example, does not concatenate versus a regular transform.
Are you talking about this and to put like a grade over here?
No, for example, if you do
like that, you mean?
No. If for example, if you do two transform mask nodes
Yeah.
after each other,
Yeah.
and you take an image and you scale one down to 1%, and you scale it up again to 100%.
Yeah.
A regular transform, because it doesn't have a mask input, and because concatenation can only work per channel, will just end up not doing anything. But a transform mask node,
would degrade it?
Because you have the ability to affect different parts of the image differently.
That's
not linear, does not concatenate.
So I'll just say something about it as well, because this is I can find it over here. This is a design by Nuke. Like, this doesn't have to be like that. There is no reason for that. I don't know why, again, they made a decision that if we have a mask, then maybe we want to do some manipulation. Same as, by the way, putting a grade over here, break the concatenation, is the same concept. There is no reason for that. We can still, I think, I don't know exactly how under the hood maybe exactly is designed, but each one of those nodes have internally its own matrix, exactly like this axis over here. And
there is a rasterization of the image itself, so
no, but
there's
Nuke
filters coming on.
Nuke
at the end of the translation.
No. What I'm saying is that for some reason, I'm saying it's the same problem with this guy over here. It's exactly the same issue. It's a design issue that this node over here will break concatenation. If I'm going to do scale down, scale up over here, it will break. We know that, right? But there is no reason, and the reason that it happens is because I guess they are going up to the parent and asking, does this guy have any metrics? Oh, it's a grade node, it doesn't have any metrics. So let's read it as a new image. And there is no reason we can actually keep on going up until we find all of them in transformation and concatenate them as well. There is no reason to do that. The only reason is when we're doing a blur, then there isn't a reason to break it. So again, it's a design issue that they decided to do. The same with this. I'm not fully on board with that. I think there is a way to do it slightly better. What I'm saying, it's not about the math in this case, but that's what I'm trying to say. It's about the design choices that they made. You know, why it's breaking like that. It shouldn't be, really, if you ask me. I might be wrong. Usually I'm wrong, so don't ask me.
I have to go to meetings.
Okay. Everybody's good?
Super good. Thank you very much.
Have a good weekend.
Thank you very much.
You're welcome.
Thank you very much.
Have a nice day.
Thank you.
Nice weekend.
Have a good one.
Bye.
Bye-bye.
Bye-bye.
Ciao.
Ciao, ciao, ciao.